Good morning, ladies and gentlemen. Our next magnetism unit concentrates on solving for the magnetic field created by a current carrying wire. To solve for the magnetic field created by the wire, not an external magnetic field, but this is the one that goes around the wire itself, we use the formula B is equal to mu naught I over 2 pi r. Mu naught is the vacuum permeability constant and is on your reference table as 4 pi times 10 to the negative 7 Tesla meters over amps. I, of course, is the current carried by the wire, and R is the distance from the wire. Okay, and you notice the 2 pi r, well, that really indicates the circumference of the wire itself. Note, however, that because of mu naught over 2 pi, mu naught is really 4 pi times 10 to the negative 7 divided by 2 pi. So a quick shortcut for this formula is to automatically cancel those out, and you end up with 2 times 10 to the negative 7 Tesla meters over amps, of course, times the current divided by the radius. Okay? And if you were to do a quick practice question using this formula, we see that an electric wire in the wall of the building carries a current of 25 amps upward. So I is equal to 25 amps. They ask, what is the magnetic field, B, 10 centimeters away? So R is equal to 0.1 meters. So B is equal to mu naught I over 2 pi r. So that equals to 4 pi times 10 to the negative 7 decimeters over amps times 25 amps. Notice the amps now cross out, divided by 2 pi times 0.1 meter, which equals to 5 times 10 to the negative 5th Teslas. Okay, but the next question, of course, would be, what is the direction of the magnetic field at that location? And in this case over here, because we're going to assume it is conventional current, then we are going to use the first right-hand rule, so that it looks like this. The thumb is the current, then your curled fingertips represent the magnetic field. Your thumb goes up, your fingers wrap around, and you can see that on the right-hand side, it's actually going into the page before it wraps around and comes back out. So it would look like this around the wire. So the answer would be, of course, into the page. Okay, so we take a we'll pause this for a moment over here. Again, we can now calculate the strength of the magnetic field at any distance away. We have a certain current that's given to us, okay, and B was simply equal to mu naught I over 2 pi r. R is the distance away from the wire itself, and you can see that technically as you get further and further and further away, the magnetic field decreases. But it's not inverse square, it's just an inverse law. So as the distance increases, the magnetic field strength will decrease as well. So technically it's never going to reach zero. It's just going to get much weaker as you get much, much, much further away. Okay, so we can now solve for the strength of the magnetic field next to any current carrying wire. Here's another example where we are going to combine both hand rules and both our formulas now. An electron traveling at 8 times 10 to the 5th meters per second. Well, let's write down our given. So an electron has a charge of 1.6 times 10 to negative 19 coulombs. A mass is 9.11 times 10 to negative 31 kilograms. It's traveling at a speed of 8 times 10 to the 5th meters per second, within a distance of 0.5 millimeters, which is the same thing as 5 times 10 to negative 4th meters. And there's a current within that wire of 12 amps. And it's within the magnetic field being produced by that current. Okay, so as it goes around, there's a magnetic field being surrounding the wire itself. If we were to actually use the hand rule, our right hand rule, we can see at the thumb points right, we can see it goes into the page and then out of the page above it. So if I were to actually draw that magnetic field, it would be into the page on one side and out of the page on the other side. They ask us first, what is the strength of that magnetic field where the electron is located? Well, B is equal to mu naught I over 2 pi r. Again, the mu naught and the 2 pi are going to cross out, so that way we end up with 2 times 10 to negative 7 times 12 amps divided by 5 times 10 to negative 4 meters. So in this case, the magnetic field is equal to 0.0048 Teslas. As we already used the hand rule, it showed that it was going into the page. Now, the next part of the question asks us, what's the magnitude and direction of the force felt by the electron? Now, the force, understand, is the magnetic force acting on the electron due to an external field. This is the third hand rule. Okay, and it involves the formula FB equals to QVB. In this case over here, the charge is 1.6 times 10 to negative 19 coulombs times the velocity of 8 times 10 to the 5th meters per second times our magnetic field that we solved for, 0.0048 Teslas, which equals to 6.144 times 10 to the negative 16 newtons. Now, using our hand rule, we can see that our thumb should be pointing to the left, our fingers should be pointing into the page, using our left hand, so our palm is going to face up. So, using our hand rule, we know the electron is going left, magnetic field goes into the page, and ultimately the force points up, according to our left hand rule. So this is a classic example of combining our first hand rule formula along with our third hand rule formula. Okay. Even if there are two wires, each one produces a magnetic field. They're asking us, in this case over here, what's the total magnetic field created at any given point? And we're going to solve for the total magnetic field of A and C. Because magnetic field is a vector, we have to solve for the direction first of each wire. Using our hand rule, and noting that, of course, the first wire, the current's going up, our hand rule go around, we can see that going into the page on the right, out of the page on the left, that means everything to the right of the first wire is going into the page, everything to the left of the wire is going out of the page. If we do the same thing with our right wire, we can see that it's going to be going into the page on the right-hand side, out of the page on the left-hand side. So keeping our red and our green here, okay? So we can see that overall, in between the two lines, between the two wires, the two magnetic fields are going opposite directions. That means that they are going to cancel each other out. So, of course, the magnetic field at point A, we're solving for the total magnetic field at point A, that would equal to B1 plus B2. But because B1 and B2 are pointing in opposite directions, they are really going to end up subtracting from each other. So as all the points 2A are equidistant and it's the same charge, same distance, the total magnetic field is equal to 0 Tesla. Easy enough. But a better question really is, what's the total magnetic field at point C? So at point C, the next part of the question, that's 3 millimeters to the right of wire 1. So it's going to be, B1 is going to be going out of the page plus negative B2, which is going into the page, or vice versa. And so if we work it out, it becomes mu naught I1 over R1 plus, or really I'll say minus, mu naught I2 over R2. So that will solve for the total magnetic field at point C, okay, which is right over there. So plugging in my numbers, I end up with 2 times 10 to the negative 7th decimeters over amps times current 1, which was 40 amps, divided by 3 millimeters away, so that's 0.003 millimeters, minus 2 times 10 to the negative 7th Tesla meters over amps times 40 amps. In this case, it's going to be 10 millimeters away, so 0.01 meters. And my final total answer will end up equaling to 0.00187 Teslas into the page, because into was stronger than out of. So this is the total magnetic field at point C. Okay. Now, just to give you another visual example of the same type of question, it's not uncommon to take those wires that are going up and give you a problem where they're coming straight out of the page instead. So if I were to draw the same exact diagram, but instead of going out of the page, they might draw, say that we have 2 current carrying wires. Each one has a current going out of the page. So using our hand rules, okay, we would have to draw what's the magnetic field around this wire that's extending out of the page. So using my hand rule, for my thumb, as it goes out of the page, I can see the magnetic field is circular and my fingers are curling in this direction. So for the first wire, it would look like this. For the second wire, it would look exactly the same. Okay, so that means that if you're talking about a point in between the 2 wires, one is going up, one is going down, and again, the 2 magnetic fields will cancel each other out. It's the same exact problem as what we just did, but this is a different visual representation instead of the wires coming straight out of the page. Here's another example, which is very often on the AP. Let's actually bring this over to the smartboard and take a quick look. We'll make up a couple of numbers over here, assuming that this first current is perhaps 20 amps. Our second current over here is equal to 30 amps. We want to know what's the total magnetic field at either point A or point B. So if you're going to do a magnetic field, you have to first figure out what's the direction of the magnetic field. So with this red current over here, if we're using our hand rule, we can see it going to the right, going into the page underneath, and out of the page above. So going into the page underneath, and out of the page above. While for the green wire over here, is going into the page to the right and out of the page on the left. It's going into the page on the right and out of the page on the left. So that means that at point A, this one, the red is going out of the page. The green magnetic field is going into the page. So therefore, we would have to solve for each one individually and then subtract them. So if we're looking for the total magnetic field at point A, that would equal to B1 plus B2. Okay? So if you work this out, this simply equals to mu naught I1 over R1 plus mu naught I2 over R2. So if we plug our numbers in, we end up with 2 times 10 to the negative 7 times I1, which is 20 amps, over 0.4 meters, plus, or really, in this case, because they're going opposite the directions, I should have written minus 2 times 10 to the negative 7 Teslas meters over amps times 30 amps over 0.2 meters. And plugging that all in, I end up with a final answer of 2 times 10 to the negative 5th Teslas, and as green was stronger, into the page. Okay, so this solves for the total magnetic field at point A. Okay. Now, previously I had skipped point B between the two wires. I wanted to save that for right now, just because it's another way of combining our first hand rule and our third hand rule together. But just to recap, to remind you guys what happens, when you take two wires and you have current running in the same direction, they're going to attract, or when they're in opposite directions, it's going to repel. And we can see the attracting and the repelling happening in this MIT demonstration over here. So right now, the way we solve for the force between the two wires, okay, we're first going to solve for the magnetic field at wire 2. So assuming that this is wire 1 over here, we're going to use our hand rule, and we're going to see that it goes, basically we have a magnetic field that goes around, and it reaches wire 2. And we know it goes into the page on the right and out of the page on the left. So the first thing we're going to do is we're going to solve for the strength of the magnetic field at that location right there. So B is equal to mu naught I1 over R1. So 2 times 10 to the negative 7 Tesla meters over amps times 8 amps over 0.003 meters, which equals to 5.33 times 10 to the negative 4 Teslas into the page. Now, the thing is, this wire is also carrying a current going down. Using my third hand rule, okay, that's this one right here, I'm going to show that because the force, the current is going down, my fingers are going into the page, I can see that my palm is pointing to the right. In other words, I'm going to feel a force in that direction. So the force acting on the second wire is equal to BIL. This is the magnetic field from the very first wire acting on the second current, and L is the length of the wire that's next to each other. So in this case, over here, our final answer would end up being 5.33 times 10 to the negative 4th Teslas times 8 amps times 2 meters, which gives me a final answer of 0.00853 newtons to the right. And because it is action-reaction, as one wire gets pushed to the right, the other wire, of course, is going to get pushed to the left, and the two wires do push apart. A shortcut to actually solve that type of problem involves understanding how can we combine those two formulas together. We have, again, as we did before, the magnetic field created by the first wire. We have the magnetic force acting on the second wire. Well, simply by substituting B in over here, they combined it into a new formula. And if I write out over here, so that means FB is equal to BIL, which is really equal to mu naught I1 over R1, 2 pi R, so times I2 times L. So it's really equal to mu naught I1 I2 L over 2 pi R. Now, you don't actually have to memorize this giant combined formula, just understand where it comes from and understand what happened. So in a multiplier question, for example, if I were to double the strength of each current, how would that affect the overall magnetic force felt between the two wires? In this case over here, if I double the strength of both currents, we can see that you end up with 4 times as much force as before. Okay? If I also happen to triple the distance between the two wires, then I would end up with 4/3 the amount of force from before.